Alright, I think I am recording and everything seems good. So, hello, first of all. Um, for this video, I thought I would tackle autodiff or automatic differentiation, um, which is the backbone of so many machine learning and neural network architectures. Um, Rather, in general, any optimization technique that requires the propagation of gradients um, would find this very useful, um, if already not. So just, I mean, apart from just explaining what the concept is or what the math is, I thought I would try doing some uh, live implementation, and see where things go. I mean, I've never done this before. Um, Actually, I might have but that was long time ago. But so yeah, I mean, um, Sunday morning, so that would be like a fun experiment to try out, and yeah, let's see where it goes. So okay, let's start. Enough talk. Okay, the point of the video is to understand and implement automatic differentiation, you know, commonly known as autodiff. Um, so, in the spirit of accessibility, I just want to state some prerequisites, just to see if this video is for you. Um, so, let me think. So, mostly high school calculus is enough, and it is true that I will be writing in Python, so the syntax might seem alien or strange if you're not um, what's the right word? If you're not familiar with programming or programming in Python, but I hope to make it as intuitive as possible. So maybe the programming won't be a big issue. Um, and yeah, so definitely high school calculus for sure, uh, but everything apart from that should be fairly simple, and obviously like curiosity, but that's a prerequisite for everything. um, okay, what next? So so one sort of rule I have when I write, or when I teach, is that um, I've obviously like learned this stuff from a lot of other places, and I think like even though I am making like some sort of tutorial, if I want to call it that, I still think there's a lot of value in going to the source material directly and not watching this, even though that's kind of not what you would expect someone to say, but I think like there are much better resources, so I just want to list them out. So in case you want to uh, get like much better rigorous understanding, you can go and look at these yourself. So okay, so to be fair to myself I would say that this video is like a distillation of all of these resources, um, but unfortunately might not be as good as any of them individually. So the first place I go whenever I'm stuck in any basic math, etc., programming, is just Wikipedia. Just open the Wikipedia page for automatic differentiation, and literally everything I'm going to tell you right now, or in the next God knows how long this is going to take, will be there. And I want to mention a very good blog that first got me, or first made me aware of such a thing as automatic differentiation. It's this blog called Graduate Descent. Uh, it's by Tim Vieira. I hope that's the right pronunciation. Mostly sure that's the right pronunciation, but I don't want to be too. Yeah. So this blog, I read it like a few years ago, and there are like two very good posts on this blog. The first one, if I can remember it right, the first one has a very clickbaity title. It's like backprop is not just the chain rule. So, okay, so backpropagation is like an algorithm that most, all neural networks use in order to learn a loss function. Or wait, what? No. In order to minimize the loss. But yeah, I just completely derailed my thought. Okay, so yeah, and so and backpropagation is usually taught in most courses, in most introductory videos, as an application of the chain rule from the output node all the way to the input variables. And this is true. This is not factually incorrect, but it is not just that, which is what we will be seeing in this video, and which is what is written much better with a lot of examples. And I remember there was something about like grandgents in this, so slightly out of the scope, even though I said high school calculus, but yeah. And then there is another one, this one I remember very well. Evaluating grad effects is just as fast as f of x. So this blog is this post has so many examples where you can just take any naive optimization algorithm and speed it up by applying an automatic differentiation sort of paradigm to that algorithm. And the best resource is, apart from all these and many more on the internet which I've forgotten or not mentioned, is Andre Karpathy's Micrograd. So this has been there for a while on GitHub, and it's like super simple. It's like, I think, less than like 250 lines of code or something, and it has everything that you just need to go through the code and you understand autodiff. And if I'm not wrong, there is also a YouTube video. So competition for me, although who am I kidding? Right, I think that is all I want to get to, and so we can start with the main thing. I don't really want to motivate automatic differentiation, but maybe like a minute. So because I think I've already spent like a lot of time on the introduction. So the differential of a function, the derivative of a function, is defined as this, with when at the limit h tends to 0. This is high school calculus. You are supposed to know this. If you've forgotten this, yeah. So yeah, you're supposed to know this. And the problem is, in cases where you're writing big programs, so analytically, mathematically, it's not a big deal to evaluate many functions just by writing the differential. So you can have like very complicated functions and you just derive everything by using the chain rule. But The thing is, with when you're programming a function and you have to differentiate with respect to any of the input variables, you're always like stuck with this um, dilemma, because doing this numerically by setting h equal to like a very very small number, let's say like, you know, 10 power minus 7 or something, it on first glance it seems like it works, but it leads to precision errors, and a lot of things can break. Many languages are not very safe when it comes to these handling these precision errors, and this is like called the numeric approach. There's another way to do this called the symbolic approach, where you just take, say you have f of g of h of x. Is that the right number of brackets? Yes. You just basically like evaluate everything, f of f dash, g dash, h dash, whatever, right? And you write this out completely, make the computer do it. This is called like symbolic, I think, in computer parlance. But it's just write a bunch of rules, expand everything. The problem is it gets way too big, way too hefty for you to handle, and you don't want to do all that. There's a much better approach which we will be talking about. So that's it. I mean, I don't want to motivate this even further. If you have looked at this, you should be sufficiently motivated. Okay, what next? So first things first, we need like a nice function to differentiate through, and let's choose one which has like a bunch of what do you call them, nice complicated functions that will truly demonstrate the strength of autodiff. So we obviously want addition, multiplication, maybe a power, what else, maybe exponentiation, a trig function. Okay, so how about x plus y times x of 3x plus y. Is this good? It has everything that we need, but I'm trying to think of what the computation graph will look like in my head so that I can make life slightly easier for myself. Right. But the problem with the problem with e power x is that the derivative is itself, so it won't get very interesting. How about something like x plus 2y square, and then you take a sine function and then you have a product inside it, right? So this is our function on which I will demonstrate autodiff. So okay, first things first, let's see how computation flows from the input variables, which are x comma y. Oops, very bad. So I'll just write this out here as f of x comma y. So we'll first see how computation flows from the input variables x, y to the final output f. So you have x here and y here, and so x and y both combine to give x plus 2y. Similarly, x and y both combine to give xy. X plus 2y doesn't combine with anything, but gives we square it, and then you take the sine of xy, and these two combine to find the final product, which is sine of xy. Okay, so this is what you call a computation graph, where you have these are the input variables, and these and in this case this is the output variable, but you can have n input variables and m output variables, like, yeah, the world is your oyster. So right, so let's first to make this slightly rigorous, what I'm going to do here is assign all of these to variables. So basically I'm going to say v1 is x, v2 is y, v3 is x plus 2y, v4 is xy. Wait, I don't need to rewrite this stuff like this. I can just do v1 plus 2v2, v4 is equal to v1 times v2, v5 is equal to v3 square, v6 is equal to sine of v4. So I hope everything is as simple as I'm making it sound. Okay, I'll just talk once through everything and I won't repeat myself again, so that we don't waste too much time. So I'm just setting each node in this computation graph to a separate variable. So v1 will be x, v2 will be y, and then v3, which is x plus 2y, can be just written as, or can just be written as v1 plus 2v2. Similarly, v4, which is xy, is v1, v2. v5 is x plus 2y whole square, but x plus 2y is already v3, so we just do v3 square. So the point of this what just happened there? I have no clue why my stylus is going crazy. Okay, as long as it doesn't interfere with my writing, I don't really care. Where was I? Yeah, so we have individual variables for each node in the computation graph. Now that we have them, I will tell you what forward mode auto differentiation is. So forward mode basically means you start from the input and you go to the output. You propagate your gradients from the input to the output. What that means is you first find dv1 by ds. S can be anything. It'll be clear in a minute. Okay? And similarly you find dv2 by ds. I know I should be saying dou because it's a partial derivative, but yeah, just it's fine. Then where was I? And then I find dv3 by ds, and so on. The partial derivative of v7 with respect to s. Okay, and so s is called the seed, and it is either going to be v1 or v2 depending on what you want the output gradient. So basically whether you want dv7 by dv1, so you want, so depending on which variable you want to find the final gradient with respect to, that is the seed you choose. Okay, and shouldn't this be a continuous document? Should I add page every single time? Okay, whatever, fine. So yeah, Where was I? It's very easy for me to lose my train of thought. Right, okay. So, and we call these each of them dv1, dv2, dv3, so on, dv7. Okay, and the point is you go from input to output always. So let's say seed is v1 as in x. I don't want it to look like I'm doing v1 of x, so just say is equal to x, right? So you want to find the gradient of every single node in the computation graph with respect to x, which is what these differentials are doing here. So that list becomes basically dou v1 by dou v1, dou v2 by dou v1, dou v3 by dou v1, so on, dou v7 by dou v1. Okay, and this is, if you think about it, dou v1 by dou v1 is just 1, dou v2 by dou v1 is 0 because it doesn't depend on y at all. Dou v3 by dou v1, if we go up, v3 is v1 plus 2v2. So v3 by, so the so dou v3 by dou v1 is just 1. Okay, and so on and so forth. This is how you do it. And if v1 is equal to y, what would happen is this would be 0 and this would be 1 and so on. So basically the first dou v1 by dou v2, dou v2 by dou v2, so on. These two things would be changed. So these are called the seed, I don't know, I forgot what the actual term is, so I'll just call them differentials. But this is not the actual term, there's something much more apt for this term. Okay, now the final exercise is for us to compute each of the dv's. Okay, so let's have these as placeholders. If we have these as placeholders, dv3 is just dv1 plus 2 times dv2. dv4 is it was xy, so that would make this v1 dv2 plus v2 dv1. Then dv5 is equal to 2 times v3, because v5 is v3 square, so 2v3 dv3. I hope I'm right. And then dv6, because v6 is sine of v4, this is going to be cos of v4 times dv4. And dv7, again the product rule is v5 dv6 plus v6 dv5. That's it. And based on whether you set this to be 0 or this to be 0, the other one's going to be 1, and these values are just going to be propagated forward all the way, and you're going to get the final value dv7 to be your true answer. So right, I'm thinking of whether there is anything else I need to explain. So should I just explain reverse mode right away and then go to the implementation, or should I just come back, is what I'm thinking. Either option seems perfectly fine, but which would be better for me pedagogically? Alright, I'll just explain reverse mode as well. And It's not that hard, so I don't know why I'm hesitating. So as in forward mode you went from input to output, in reverse mode we come the other way around. So we come from the output to the input, and there's one small sort of technical difference, which is that now you set the variable that you are going to find the gradient with respect to the same. Okay, I sort of, spoiler alert, I gave away the answer, but you set the seed for everything, and then you just find the gradient of the seed with respect to every single node in your computational graph. Okay, so instead of scrolling up and down, I'm just going to show you what the difference was with respect to forward mode. In forward mode, we basically had dv1 by dvs, dv2 by ds, and v7 by ds. So this was forward mode. So, and this is reverse mode. You see, it looks like reciprocal, but it is not actually the reciprocal. What's actually happening here is that in forward mode, we choose an input variable as a seed, and we find how much perturbing that one input variable changes the entire computational graph. In the reverse mode, what we do is we choose we choose the output node, and we find out how much every single node in the computational graph affects the output node. So this is the fundamental way that they are different. So I'm just going to undo all this so that it doesn't get too confusing. And because these are sort of reciprocals, we give them something else as a notation, and these are called adjoints. So these are gv1, gv2, gv3, so on, gv7. And we can just have one-to-one explanation here. And like I said here, again, S is seed. And this time, because there is only one output node, the seed has to be v7. But doesn't have to be. You can technically assign 6 as v6 as the output node, and then you would find the gradients of every single variable or compute graph before v6. Right, what else? So let's assume seed is equal to v7. Now all those things become v7 by v1 do v6 by 7 by, yeah, it's slightly confusing even to me, even though I've done this a bunch of times. Okay, and this is so this part goes to 1 this time, and everything else is computed in a similar sort of fashion. So I'm going to leave the computation of compute GIs. Okay, so right. And is there anything else that I have to say? So GIs will basically look something like this, but not really. They will have the same structure, but they'll be slightly different, and you have to really think about what is happening in the computation graph before you before you calculate the GIs. So just be a little bit careful. And okay, so I've had enough of writing on this thing, so let's do some cool stuff and move on to writing some code. Usually this is where I mess up, but let's hope the gods are smiling on me. Okay, so terminal, cd into this. So first we will implement forward mode autodiff, and right. Okay, so is this font big enough? Okay, I'll just make it slightly. Okay, this is too big for me. Okay, good compromise. Okay, so our function was fairly simple. We just had to, so maybe I write, what was it? I forgot. X plus 2y power 2 times sine of xy. Okay, so what we're going to do is we're going to create this computation graph, but now it won't be like a graph, it will be just like a bunch of nodes for now. We can get to that stuff later if I still have the energy by then. So v1 was x. You can just go back and see where was that. Oops. Yeah, here. V2 was y. V3 was v1 plus 2 times v2, and v4 was v1 times v2. v5 was, I'm assuming, v3 square. Then v6 was sine of v4. Yep. And v7 was v5 times v6, and we return v7, and yep. So let's initialize x val to be 2.0, y val to be, I don't know, 3.0, and okay, let's write out the entire print statement. Value of the function, always make this mistake, at is f of x val, y val, and then we close this bracket, close the f string, close the print, and we should be good to go. Oops, what have I named this f value? This is supposed to be okay. So we have this nice function that returns its value, and we have all the individual nodes. So now how would we think of writing the differentials? We can just write them here. So maybe for now I just get rid of this, and we could just have a bunch of numbers like this. dv1 is equal to 1, dv. So as you can see, I have already seeded these to be 1 and 0. In general, you can have like an argument to do that, but just for the sake of just for this video, I'm just running through it quickly. And actually, a clever way to do this would be to have an argument here that just asks whether you want to even return the gradient. So if no-grad is true, then you just return v7, and otherwise we compute the differentials. So basically, if we don't want to compute the gradients, we just return the value of the function, otherwise we will compute the gradients. So I am not at all interested in typing all this again, so I'll just yank all these and paste, and this should work. Yep. So dv1, let's seed this to be 1 first of all, and dv2 we can seed this to be 0. dv3 is dv1 plus 2 times dv2. dv4 is v1 times dv2 plus v2 times dv1. dv5 is 2 times v3 times dv3. dv6 is math cos v4 times the differential of 4, v4 I mean. v5 you go v6 times dv5, and you say dz by dx is equal to dv7. Okay, and I can just basically repeat the same stuff exactly, and all I need to do is seed these the other way around and need to say this is dz by dy. And finally, after all this is done, I need to return v7, which is the output of the function. I need to return the differential with respect to x and the differential with respect to y. So okay, now okay, let's should I really type all of this again? No, just once is enough. Value of, actually no, partial derivative df by dx at this is x val y val false, and we have to index the first number in the tuple. Am I doing it right? Yes. Anyway, I mean, if I do it wrong, I will get an error, so I don't need to waste my time thinking about these things. And then finally R2 should work. Okay, so we have numbers, but how do you know if this is correct? So let's quickly just write, let's close this and write a function called ftest. I'll try and do this as quickly as I can so that we don't have to waste time. So def fxy is return math.sign. I'm doing the sign because I don't want to run into any sort of hierarchy, I don't know what that's called, arithmetic operator hierarchy issues. Then df by dx is, oh, I have to calculate this, don't I? Let's do this. So what would dou f by dou x be? It would be 2 times x plus 2y sine x y plus cos xy y x plus 2y whole square, and df by dy is going to be the exact same thing, except this is going to be 4 because 2 times 2 is 4, and x plus 2y sine of xy plus, and here this y is going to be x, so cos of xy x plus 2y whole square. Just double checking if I'm right. Yeah, should be correct. And if I'm not, I will find out pretty soon. So here df by dx, I don't want to write all that in a single sentence. So 2 times so this is the first term, and the second term was y times math dot cos x into y times x plus 2y square, and I return a plus b. Did I make any errors? 2 times x plus 2y, right? Math sine y, math cos x plus 2y. Very good. Now all I need to do is yank all these, paste, and change the variables. This was 4 if I remember, this was x, and yep, I'm good. So okay, x value was 2 and 3 if I remember right, and then not more print statements. So okay, but I just have to do it once, so let me not complain. Xval and at yval. Is this right? Yep. Now I need to go df by dx at this place is literally df by dx. This was simple. Oops. Df dy is df dy, and then I go Python 3 ftest. Are these the same values? Minus 17.88, 179. Yep, these look the same. I mean, completely the same. So we have this ftest to help us whenever things look slightly off. But also the good thing is, I mean the cool thing is that our forward mode algorithm worked. In fact, this is all it is. All you need to do is find the values of every single node in the computational graph, like we do here in this block, and for each computation node, just find the gradients with respect to whatever variable you've seeded with. So here we seed first with x, so maybe I write a comment seed equal to x, and then oops, right, and that's all there is to it. So this is what is, so this is like the interleaved approach, where you basically, so you, instead of writing another entirely new algorithm to compute the differential, or writing a symbolic algorithm where you have to completely expand everything, now you just, for every single operation, you have another line of code that in probably this almost similar number of multiplications and additions computes the gradient for you, and that's a great thing. The not so good thing is the fact that for every single input variable we have to run a sweep through the entire graph. So for example, when we seeded it with x, we ran a sweep, and when we seeded it with y, we ran another sweep. So basically, then if you have n input variables, you run n sweeps, which is obviously not ideal, but we'll get to that later. So this is one way of doing it. There's another way of doing this. So I'll just go back. So there's another way of doing forward mode auto differentiation, which is called you know what, first let me add like a bunch of pages, 1, 2, at least 2, hopefully we use them. So there's another way to do forward mode auto differentiation, which is actually a lot more cooler. So I just want to show it. I think this will take like at least like, this will take a while, but maybe I'll go through it much more efficiently than I did the last 1 hour, or I don't know how long I've been talking. So the approach is called the dual number approach, and this is so cool. This was, I think, invented by a dude named Clifford or something. If I'm wrong, definitely come for me, because I shouldn't be forgetting this stuff, but yeah. So dual numbers are super interesting. So they not only have so every dual number has a real part, and oops, that was my alarm. Every dual number has a real part, and also a dual part. Okay, and the definition is that, so just like imaginary numbers are written as a plus bi, where where I square is defined as -1. Here you have a plus b epsilon, where epsilon square is defined as 0. That's all. This is the definition, and do with it everything that you can, is the whole idea of dual numbers. Okay, now the reason this is important, so I'm not gonna like go into the math of all this, but the reason this is important to us is because it has a very nice property, which is that if you have a function f of x, any function f of x, and if you compute f of x plus epsilon instead of f of x, you will get f of x again plus the derivative of the function at x times epsilon. Okay, so so this, oh god, I can't draw to save my life. Actually, no, I can. So this property is what is leveraged to make this work for forward mode auto differentiation. So I'll give you like a few examples, and this will make it like so cool. Let's say f of x is, I don't know, 3x plus 2. we continue with our fascination with 2 and 3, the first two prime numbers, so why not? So to get the derivative of this function, just do f of x plus epsilon. So this will make it 3 times x plus epsilon plus 2, which is 3x plus 2 plus 3 epsilon, right? Now this, like I said, is, so this part is f of x and this 3 is f dash x, and yeah, that's why it's so cool. And if you want to be like slightly pattern matchy in your thoughts, you might have noticed that f of x is f of x plus f dash x epsilon, and this means f dash x epsilon is equal to f of x plus epsilon minus f of x, which is very similar to what we started off with, or I hope I spoke about it, the definition of a derivative. It's very similar, but just be very careful. This is not at all the same thing, because you can't actually bring this epsilon under the f of x plus epsilon minus f of x to divide, because zero division is not defined in the ring of dual numbers, so it doesn't have zero division, so you can't do this, but it's like nice thing to look at. So this is an aside, completely irrelevant. I don't know why I brought it up. So let's choose like a slightly trickier, maybe not trickier, we don't want to waste too much time. Let's choose like a quadratic. So f of x is equal to, no more 3's, 7x square and okay, maybe a 3, right? So now f of x plus epsilon is, if you do the math, okay, I'll just write it out. So this goes out to 7x square plus 3x plus 4 from these, plus 7 times 2 times epsilon times x, which is 14x, plus 3 times epsilon plus 3 epsilon plus 7 epsilon square. And from definition we know that this goes to 0. So this is f of x, this is f dash x, and we know analytically that the derivative of f of x is 14x plus 3, which is what we get. Now how do you actually code this out? It's again like super interesting, super okay, I've run out of adjectives. So save this and let's call this dual number example. So the way you code up dual numbers is by overloading the Python operators basically, and so you have like more functionality added to them. So every dual number has a real part and dual part. This is what I've written here, and doing some Python stuff. Wait a second. So this is just initialization. Every number will have a real part and a dual part, and so what I can do is just initialize a number to 3 and 0, and maybe print and 8 or 2, so I hope this works. I've not done this stuff in a while. Yeah, it does. Why shouldn't it? So now this is how you have a dual number, and so now it doesn't really have like much of functionality, so to speak, but we will add, like, let's say we add addition. So the way you add addition is by overloading the Python add operator. So for those of you that are not well versed in Python, just yeah, I mean, it's, how would I explain this to someone who doesn't know Python? Okay, so what I'm doing right here is taking apart the idea of usual variables in math or programming and adding another part, dual part. And you don't need to do it with this sort of class sort of way, but it's just easier to do it this way, and that's why I'm doing it. So TLDR, every number from now onwards is going to have a real part and a dual part, and the way I'm doing that is by using something called as an abstraction called as a Python class. And the way, and because rules of addition and multiplication are much different in the dual number space, I'm going to have to rewrite the very rules of addition and multiplication, which is what you will see now. Okay, so the real part, so let's say you're adding two dual numbers. Let's say you're adding a plus bi and c plus di. The real parts just get added, a plus c. So that's what you do here. Self.real plus other.real. And similarly, the dual parts just get added together. And you just return so the reason I return dn of real dual. So also for people who know Python, all this is going to sound like I'm beating a dead horse, but I'm just trying to make this thing accessible to everyone. So anyways, so the reason I'm returning dn of real dual and not just real part and the dual part is so that now so basically I'm returning a dual number in itself and not like a collection of two numbers. Yeah, I don't think I've done a good job, but okay, whatever. So now let's test addition. So you have a number a and let's add 3 to it. Okay, what do you think is going to happen? Right, so this is a very informative error message. I mean, I knew this would happen, but I just wanted to show it. So it says the int object has no attribute dual. So what we're trying to do here in line number 13 is take a dual number a, which has been initialized as a dual number, and we're trying to add a normal integer to it, which won't work. So what we need to do is we need to convert 3 to a dual number before we add. Or, because that's not always feasible, like when you're dealing with real world functions, you just can't say just because I have a number I'm going to convert every single number in the entire function to my choice. So what you need to do is basically handle it right when you're working with it. So I'm going to check if the other number that you're going to add is already a dual number. This is the code that you would write, right? Like whatever we just wrote. But if it is not, what we do is, so the real part is the self.real plus just the other. We don't have a dual part for the other number, so we don't care about it. And the dual part just stays as it is. It's almost like adding 0 to it. You get it? Because there is no dual part for any other number. And so I just do return dn real dual. Okay, now this is going to work. Okay, so because 3 went in and it found, so the compiler basically went, okay, it's not a dual number, so I just add the number to the real part and do nothing to the dual part, and it converts it to a dual number at the end. Now let's do one last error check. let me do C is 4 plus A. And okay, now we're gonna stumble upon another error here, which is unsupported type. It's not very informative, as most error messages are. What's actually happening here is it does not support, so it's a very strange Python quirk. In fact, I think other languages have it too. But what is happening here is that if there's a dual number on the left side of the operator, it will add whatever you tell it to add from the right side. So A plus 3, A plus anything works, but something plus A will not work because it wants the first number to be a dual number. The actual reason for this is because under the hood, what is happening is C is becoming 4 of A. So this is what is happening when, oops, why did I say mul? We're jumping ahead here. Add. So the line number 19 is actually translated as 4 dot add A, and 4 goes to the self part of the when you're initializing, and A goes to the other part. And so it's like it tries, and basically the only error checking we've done is for other. So instead of writing another if statement, all we need to do is add this nice line here, which will make it work. And so now we should get 3 0 6 0 and 7 0. It works, all good. Now addition is done. I would like, you should sort of like pause and write multiplication on your own, but I will still write it here. So first what we do as usual is we check if both numbers are dual numbers. Oops. And if they are, then we do self.real times other.real, and dual part is self.real times other.dual plus self.dual times other.real. Is this correct? Should be right, because when you do A plus BI times C plus DI, A, B get added for the real. Why am I saying I? You mean I know, you know what I mean. And the coefficients of the epsilon part get cross multiplied. So it's basically self.real whatever. And then obviously you return else. What happens is real part is just self.real times other. Oh, what happened here? I must have touched my trackpad or something. And dual is self.dual times other. It's almost like treating other.dual as 0, because there is nothing there. Okay, and dn real dual, and obviously our mul. Right. So let us initialize another number, maybe 4 2, and we make E to be, let's test multiplication, and then create another dual number, and let's test dual number multiplication. Okay, now all I need to do is just yank this and paste this 4 times. Yeah, bear with me while I do this. Oops, I missed that there. There we go. So D was 4, 2. E was D times 3. So 4 times 3, 2 times 3. F was 6, 2. And D times F is 4 times 6, 24. And then 6 times 2, 12. Plus 4 times 2, 8. So 12 plus 8 is 20. All of this works. And then finally, we will do some exciting and now the differentiation stuff. So let us define our function as we were talking. What was that? X. Okay, so return 7 times x plus 3 times x plus 4. Okay, and diff of fx is going to be, like we discussed, we just have to put x plus epsilon in place of x. So how simple is that? Return in f of, initialize a dual number with value x and dual part 1, and we have to return its dual part because the real part contains f of x itself and the dual part contains f dash x. So now let's print f of 1, and this is going to be f of 1, and then let's print df of 1. Yeah, I mean there's too many d's and f's, so I'm just completely confused. f1, right, so yeah, there we have it. We can just check if we want. When we substitute 1 in this function, we get 7 plus 3 plus 4, which is 14. And then when we substitute 1 in f dash x, we get 14 plus 3, which is 17. And that's what we get here. So maybe I print this again. So f of 1 is 14 and df1 is 17. And that's all. So you see how easy this gets now? All we need is a function. And once we have the function, and once we have dual numbers, we just need to substitute dual numbers in place of the input variables, and we get the gradients. And yep, that will be our next point of order. So I'm just going to close this stuff. So what do we need now? So right, so I already have a file called f, so I'm just going to move that over to let's call this just interleaved.py, and then I'm going to open another, let's call this dual.py. Okay. I should probably just be able to just get all this, and instead of rewriting everything. Okay, so we have the dual number class. So we have to remember that the function that we are working with is still the what was that, fmad interleaved. Oh, I think I can just get rid of all these lines now that so here I just take all this, and yeah, I don't need this also anymore. Oops. Oh. So here we don't care about no grad part anymore, and Very good. We might need one last thing. The print statements. I'm absolutely not going to write all of them again. So, yep. And for now, I'm going to set all this to none. And I'm just going to check if this file runs. Yep, works well. So we can start. We can move on to more useful stuff. All right. How shall I go about this? How shall I go about this? I'm just thinking, we already have add and multiply. So maybe first I start by defining the function again, but this time for dual numbers. Let's say we take in x dual and y dual. So v1 is just going to be x dual. Okay, this is going to be horrible to write again and again. Maybe I can just copy this stuff. Right. So v3 is the same, v4 is the same, v5, v6, everything. No. So v6 we have to work on, because actually even v5, right? So let's start with v5. So v3 is just addition and multiplication, we've already implemented it. v4 is just multiplication, we've already done that. v5 requires a power, so now we need to overload the power operator, and the way we do that is just very similar to how we've been. So we have a number and its power. The real part is just self dot real times power, and the dual part is power times actually I just want to work this out before I do something wrong. So let's say f of x is equal to x bar n. What is this going to be? This is going to be the binomial expansion from I equal to 0 to n choose I, x power n minus I epsilon I, and this is just I equal to 0 to 1. So because from e square onwards everything is 0, this is just n choose 0 x bar n plus n choose 1 x bar n minus 1 epsilon. So this is just x bar n plus n x n part. This part is the real and this part is the dual. Okay, so power times self dot real times, not times but power, and we multiply this whole thing with self dot dual. Correct, yep. And now I just return so power is also done, and now we need to have sign But we don't need to overload this, we just can have a different function. Let's say we have an input variable d. The real part is very simple, it's just math sine d dot real. The dual part is where we struggle, and so back to the drawing board we go. F of x is sine x, so sine of x plus epsilon is come on, sine x cos x plus cos x sine epsilon. This is correct, isn't it? Okay, now right, okay, I got it. So the expansion of cos x is 1 minus not cos x, cos epsilon is 1 minus epsilon square by 2 factorial plus epsilon power 4 by 4 factorial, etc. No, plus so on, which is equal to just 1 because everything after this is 0. You know, everything after this is 0. And similarly, I mean, I don't want to draw like an arrow, but okay, whatever. Similarly, sine epsilon is equal to epsilon minus epsilon by 3 factorial. Yeah. Wait, is this sine or... Okay, I mean, yeah, this is it. Plus so on. This is equal to epsilon because all these go to 0. What a horrible arrow. Go to 0. So basically, sine of x plus epsilon is sine x times 1 plus cos x times epsilon. And that makes sense. This is f of x, this is f dash x. Nice. So the dual part is math.cos d dot real times d dot dual. Very simple. And then I return dn of real and dual. Yeah, I was just taking a break because I've been talking for so long my throat hurts. Now, having done all this, we just need to now make this sine, almost wrote sundial. Sine dual of, what is this, V6 is okay, so this is V4. Nice. So now we have dual functions for everything that we need. All we need to do is write the forward process. And this is like the simplest thing after all the hard work we've been through. We have a function, we have x, we have y, and let's say, depends on what you want to seed it with. Let's say you want to have let's say you want to seed with x. Okay, so as always, seed is equal to x. Okay, so when you seed with x, what you need to do is the real part of x is just x, and then the differential, the gradient, you have to set to 1, and setting the gradient of a dual number is equal to setting the dual part of it to 1, which is what we do in this line, in this line. We set the dual part to 1, and similarly when we have to set seed to y, we have x dual is equal, I'm allergic to typing stuff again and again, so I'm just going to paste. This is 0 and this is 1, as simple as that. Now once we've had the seeds, all we need now is df by dx is just take the function send x dual and y dual to it, and take the dual part of it. So the function will give you both the real and the dual part. The dual part is the gradient, that's what we care about. And similarly, df by dy is equal to function send x dual, send y dual, get the gradient by just extracting the dual part, and then I return df dx, df dy. Now all this is done, so I just need to call fmad somewhere, so I'll do that here. Df dx df dy is fmad. Here I need to send in z dual and x val and y val. Okay, and here I just need to df dx, df dy. Let's see what happens. So I don't remember if these are the same numbers, but should be the same numbers. Unless we messed up something really bad. Fmad interleaved. So yep, they are the same numbers, yes, and that's it. Like, we got it done. So to recap, once we have the dual numbers, all we need to do is send in a dual number as an input to a function, and the function's dual part is the gradient of the function. So knowing that, what we do is we write whatever function we are interested in, then we initialize the dual number, the input variables as dual numbers, and then we just send those dual numbers into the computation graph. Instead of usual real numbers, we just send the dual numbers into the computation graph, and the final node in the computation graph has a real and a dual part, the dual part of which is our gradient with respect to whichever seed we have chosen. And that is all there is to forward mode automatic differentiation. Like, by now, like, you should be able to like code up like anything. Like with exp, it's like fairly simple. You just need to have because the differential of an exponent, the differential of e power x is just e power x, so that's not very hard. Trig functions we've already done, powers we've done, logarithms something to work on. Yep, and so this is all there is to it. Now, like I said at the beginning, the problem with this is not the fact that it doesn't work or anything like that. The problem is, let's say you have n inputs, and you do a bunch of stuff. This is a computation graph, and you get one output. The problem with forward mode automatic differentiation is that for all n inputs, you have to seed n times and run the whole graph. It's called a sweep. You have to sweep through the whole graph n times. So it's like very, very computationally inefficient. Like, you don't want to do it this way, especially when the output is just one unit or one node. What you would rather have is to have the output as the seed and go backwards, so that no matter how many inputs are there, you just have one sweep through the graph. And in practical settings, especially in machine learning and deep neural networks and stuff like that, the latter case is more common. We usually have like huge, very high dimensional data going into extremely large neural networks, and the output is just like fairly small. Like, we are trying to classify maybe 1 to 1,000. In sometimes we're just doing a 0-1 classification. Sometimes it's just like I don't know, you're just trying to predict one word from the vocabulary. You get it? It's the output is usually like very small compared to the input, and so it makes no sense for you to just seed a different input variable every single time to compute the gradient. So in practice, for neural networks, for deep neural networks, what is usually done is something called as the reverse mode automatic differentiation. And you can do this a bunch of ways. You can do this the first way by just interleaving, uh, like we did for this, in this example on the right, where we just have a function, and with every line of propagation through the graph, we also propagate the gradients along with it. I know these are written two separate ways, but you can just write one after the other, which is why they're called interleaved. So this is one way you can do it, but it's not really flexible if you think about it. It doesn't, like, for every function you have to rewrite the whole thing again. So what basically a lot of these automatic differentiation libraries like PyTorch or TensorFlow, Yax, I think, does this, or whatever you can think of, right? What they basically do is, they, for every function, they have a bunch of they decompose every function into a bunch of operations. They create a computation graph, and they perform a topological sort from the back node. So in our case, let's rewrite our example. Right, we had x, y, x plus 2y, xy, okay. Now you start from the output node, which is v7, this one, and what you do is you check, and basically you reverse the direction of the graph. So the forward pass goes this way, and the backward pass goes this way, right? So I'm just reversing the gradients. Doesn't mean this is just flow of gradients. This is not flow of data, right? So goes like this. Okay. Now what happens is you start with v7. This is called the seed, which is the output node. You start with v7. You check if v7 has any children. v7 does not have any children, so you just move on to its parent nodes. Now you go to v6. v6 has one child, and what you need to do is basically add the gradient with respect to v6 of v7. So that's basically like x plus 2y whole square. Similarly, v5 has v7 as a child. Now what you need to do is you need to add to v5's gradient the gradient of v7 with respect to v5, which is sine of xy. Okay, so what I'm saying concretely is dv7 by dv6 is x plus 2y whole square. So this thing is added to the gradient of v6, and similarly to v5, so on. Similarly, you have v3, v4, and then when it comes to x and y, these are slightly special in this case because they have two inputs. So x has two children, both v3 and v4. What we have to do here is find the gradient here, and then add both of them, and add the entire thing to the gradient of x. This is what happens under the hood. And I'm wondering if we should code this up. Yeah, I mean, I think we can. For this function at least, it's going to be relatively simple. Yeah, but this is definitely a little bit, slightly going to be a little bit advanced because it deals with like graph traversal and stuff. But apart from that, it should be okay. So I just want to create so I go right. So how do we start off? Like I said, the first thing we need is a graph, and a graph has a bunch of nodes. So and every node will have a value. What else can we do? So for now, self dot value is equal to value. Obviously every node will have a gradient. For now we can set that to 0, and every node will have children. We can store them in a list, and let's, for the sake of because this is going to be a little bit involved, let's have names for everyone so that we can debug easily. Okay, and yep, that is it. So I'm just thinking if I should implement anything else. Nah, that's good. I mean, that's good for now. So x val was 7.0. I mean, sorry, 2.0. Where did we get 7? Oh, the function. Y val is 3.0. Now I'm going to create v1 node with value of whatever xval has, and I'm going to name it v1. Okay, similarly I'm going to create v2. This is going to be yval and name v2. Oops. And let's print v1 and v2. Okay, I mean, it's going to be printed as an object or something, so maybe like value two, 3. Right, so we have it working, but it's not very nice. So what I'm going to do is I'm just going to do some more Python stuff. So basically I just want to have a better way of printing all this. More f strings, as if we did not have enough of them. So value is just self.value. Grad, okay, let's print grad as well, and also let's print name. And yeah, children we can just, I mean, we don't really care about at the moment. So now when we print v1 v2, it should be 2 0.0 and the names, so v1 v2. Nice. This looks much more official. I'm thinking what else now we need to do. X plus 2y. So we first need to multiply 2 and y. Okay, so I see what the problem is going to be. Yup, I see what the problem is going to be. So I just thought of a problem, which is that if you try to do x plus, so if you just try to um, say do v3 is equal to v1 plus 2 times v2, and even if we implement addition and multiplication, okay, maybe just let me do it instead of talking. V3. So I'm going to define addition and maybe I'll redirect it to another function. Oops. So I'm going to define it. So if I have two nodes, and let's say the final name is going to be none for the the result of the addition, we just need to check first, like we did last time, if node 2 is a node. If it is, we have to just add the values inside them. You get it? So I might not be talking as much as I was because this is fairly uncharted territory. So, but okay, I mean, I got it. So right, so when we add, we just add the values in the nodes. We don't do anything else. And what we need to do is we need to append these two nodes to the children. So node 1, node 2, and then if not, just node 1 dot value plus node 2, because node 2 does not have a value. And then I'm not sure if I need names here, because how would I even give it a name? What a waste of time, ain't it? Yeah, I'm just gonna get rid of this. Yeah, I mean, it's okay. I can manually name it later. And then out dot just node 1 this time, because if the second number is not a node, that means it's like probably like a constant or something, and you don't really care about finding the differential with respect to a constant, so you don't need to add that to the children. And I just return this thing. Right, similarly I'm going to do mul very quickly. Yank, paste, and then this is going to be node 1 value times node 2 value, and add these two, node 1 value times node 2, and then return out. So multiplication is done as well, and here I just need to do and right, so multiplication is done, addition is done. Now it should work. And for good measure, we can also just print out the children. So print children of v1. How would I do this? Children of v1, it's a list, so I do children dot name for ch in v1 dot children. Yep, that should work. So here I go R3, R2, R2, R3. Okay, did this work at all? 2, 3, so 2 plus 6 is 8. So V3 did work, but the children of V3 should be V1 and V2, and that did not happen. Why? Why? Okay. So what happened here was, so V1 is a node, so it got added to the children, but 2 times V2 was probably not. Oh, I see. It is a node, but it doesn't have a name, so which is why it has been assigned as none. So if I want to see it here, what should I do? You know what? I'm just going to create an intermediate variable, call it 2 times v2, and give it the name and also I have to name v3. Oops, didn't work. This has to be yes, now it works. So the multiplication is done well, and the children of v1, there are no children. Children of v2, no children. v3 has v1 and v2i. Also note that this is just the forward graph, so which is why the children are like reversed of what I explained while I was writing. Okay, so multiplication works, addition works. What is next? v4 is v1 times v2, and I'll just name it for good measure. And okay, so we've added v4 as well. So you can see v4 has a value of 6, which is 2 times 3, and the children are v1 and v2. Very nice. Our graph is coming along very well, but now for the first time we run into problems, which is v5 is equal to v3 square, and v5 dot name is equal to v5. Now we need to work on this power operator. no fear, we've done it once. Self power, and I will return power of self. Oh, I think shouldn't this be other? Okay. No, this has to be node and exponent. And I don't really care about the name. So here we just do node power exponent. So basically the value in the node, power to the exponent, and we have to just add one value here, which is just node, nothing else, and we return out. So v4 becomes v5 as does it here. Okay, so we have v5 as well, which is v3 whole square. 8 square is 64, and the children of v5 is v3. Okay, and now we need to do sine. Sine just has self because it's just a math function. Return sine self, and we just add that here. Node out is just the value in the node, the sign of the value in the node, and then the children are just node again, and then we return out. And then we go and add this in the variable list, which is sine of v4, and then give it a name, and we can do v7 because we've already implemented multiplication. So this, it becomes v7, v6, everything should work. Okay, the final value is right, minus 17.88. We've been getting that all the time, and all the children also look correct. Okay, so the forward pass is done. So we have a graph now, and we have a forward pass. So I'm just going to comment out all this, and now we need to think about basically how we back propagate through this graph. Okay, how would I go about starting this? So let's say I start off, and I need a seed obviously to start off with, and I need to set this gradient of the seed to 1.0. What I need a set to check if I've visited a node. and I need a queue to basically visit all the nodes. And what I need to do here is while queue is not empty basically, so the node is going to be the first element in the queue, and if I have not visited the node, I just need to add it to visited, and for child in node.children I need to add them to the queue. Right? So when the queue is not empty, I take the first element in the queue, I check if I visited it. If I have, move away. If I have not, I mark it as visited, and then I add its children to the queue for later checks. Okay, this works. Just for a sanity check, I'm going to print queue. But queue is going to be empty if I do this right, so it makes no sense to print that. I'll print visited, and I need to call backward. With seed as v7, right? So if I've done this right, I should get v7 and then v5, v6, whichever order, then one of v3 or v4, and then v2, v1, if I've done this right. Okay, so what just happened here? Okay, it's printing every single node, huh? So I just need to print the name. Whoa. I convert this to a list, and add a square bracket to do list comprehension, n.name for n in this. Okay, nice, this works. So I'll redo this. v1, v2, v2i, v3, v4, v5, v6, v7. Yep, we got what we wanted. Why is v2 at the end? Whoa. Oh, okay, so this set does not actually support order of insertion. That's not ideal. But okay, why would that stop me from just having my own list? And I just need to do visit list dot append node, and this time I just need to do right. Now we have it, v7. I'm just gonna run this a few more times before I celebrate. Okay, this should work. Yeah, it's a list. So v7, v5, v6. So it starts at v7, picks v5, v6, adds them to the queue. Then v5 has v3, then v6 has v4, v3 has v1 and v2i, and right, and then v4 has v2, I think, or something, whatever. But we have the list now. So for every node in visit list, I need to, okay. This is getting very annoying, isn't it? So I need to have a, so what is, okay, I'll tell you what is happening in my head right now. So when you start with v7, which is what you start with, V7 has come about because of a multiplication between V5 and V6. And the only way we propagate a gradient to V5 and V6 is if we know that V7 has come about via multiplication. And right now we don't really carry that information anywhere, right? How do you know that V7 is a multiplication? Like, where have you written that information? So I need to have another another sort of, whatever you call this, method, parameter, whatever. And so for addition, I'm just going to make this equal to add. For multiplication, for power, and sign. Yeah, am I doing this right though? What is my plan after this? Okay, so my plan is basically to just go shamelessly just write if statements. That's it, right? Or is there a better way? Okay, I mean, it works. Surely there should be some better way, but that's fine. I mean, this works very well. So for addition, all you need to do is multiply the gradient by 1, because that's all addition is, right? So if you have x plus y, differentiate by x, you get 1, differentiate by y, you get 1. So all you need to do is multiply the gradient by 1. What I am worried about though is that not all, so some nodes have different numbers of children. So I need to find out, oh god, another if statement. Okay, so at this point my code is getting very bad, but I have made this bed, so I have to lie in it. If there are 2 children, which is the max in our example, but this is definitely not going to work in cases where there are 3 inputs or something. So yeah, something I need to work on, but just for the sake of showing you. So the gradient of the first child is going to be just the gradient, its gradient, times 1.0, and second child is going to be, that's that. Oops. And there we go. If it is multiplication, this is slightly tricky, but in essence I can still copy up this stuff. Only this last part changes. I should be able to do some sort of multi-line editing here. Nice. So for the first child, the gradient is multiplied with the second child. So if you're doing xy, differentiate with respect to x, you get y, differentiate with respect to y, you get x. So this is what is happening here. And then so yep, very nice. else am I missing? Actually, this doesn't work here. This just has to be other. Something else. Right? Because there is no such thing as the value of the other object when it comes to a constant. So, okay. So what I need to do here is, and then I need to go to mul, and in case there's just one, wait, let me think about this. Yeah, in case there's just one, I need to do out dot other is equal to node 2, so that if there are constants, it gets multiplied. This should work. Then, yeah, I'm just realizing that we also need it for power, so I'll just show you why that would happen. So for power, like, we have a base and an exponent. The base is just like the child, and the exponent, we actually don't know what the exponent is, which is, so for that we need to carry that as well. So we need to store out dot other as an exponent here, and we need to use that here. And then so I'm just thinking what would happen here. You would have to do gradient times exponent times the value. Okay, first just do gradient times n times x bar n minus 1. So exponent times wow. Okay. At this point, I have given up trying to explain what I'm doing and just doing it for the fun of the game. If it is a sine, this is far more easier than everything we've done the last 2 times. We add the gradient, obviously, times math dot cos node dot children 0 dot yikes man value, and that is that. And what else do I need? So I run backward with seed equal to v7, and then I need those files. Oops, abort. Hopefully interleaved is not open. Yep, I need this stuff. Need these print statements. Nice. Okay, I don't need you anymore. So value of this function is just v7 dot value this is v1 dot grad, and this is v2 dot. Bolt. Yep. Where have I missed? Oops. I've missed it in a bunch of places. Used to C programming. Wow. I just did not believe this would work. I was sure I'd messed up the gradient calculation somewhere. But it does work. Strangely enough. Let's just print out all the values as well. Oh, wait, no, not this. No, I do need to comment here and not here. Oops. Okay, so this is where the instructive value peaks. So ignoring the numbers, we can see that the computation graph has complete gradients and values of every single intermediate node. So 2, 3, 8, which is 2 times 2 plus 3, and then 2 times 3, 8 square 64, sine of 64, sine of 6 maybe actually. Yep, this, and then the final value 64 times minus a quarter or something ish. And the gradient you start with v7 as 1.0, and then if you see the gradient of v6 is just the value of v5, the gradient of v5 is just the value of v6 because they're multiplying, and then v4, v3, v2, v2, it just propagates like that. And so all you need to do is now you just have to, for whatever value you want, let's say you take 6 and 1, you get what? Why is it the same value? Have I made a mistake? Whoa. 6. Oh. Unbelievable. I chose a function that would give the exact same value because of so 6 and 1 end up with 8 and 6 because 6 times 1 is 6 and 6 plus 2 is 8. The same thing happens with 2 and 3. Wow. Is that the only combination that would give? Anyways, yeah, but you see, right, all you need to do is change the values and the gradients propagate, and that's it, we're done. We've created our own sort of mini autodiff. This is something like what PyTorch does, but obviously much more elegant, much more versatile, much more flexible. And yep, I don't know how to end this, but I'm super tired, so I think this is a good place to stop. For the best learning value, I would say just once you're done, if you're still with me, I mean, awesome, thank you. And for the best learning value, just close this, like spend a day doing something else, and then try and write all of this yourself. That's the best way to learn this, in my opinion. Yep, it's as good as any time to stop. So I will stop.